can set a time.
Oh, I pressed something.
You do not press anything. You do not touch it.
All right, so it's time.
Good.
Okay, please sit down if you're entering. Go, we're starting right now. I don't need this thing by the door, right? Yeah, no, it's fine. Okay, so we're gonna be starting with the next talk right now. So please sit down, take your seats, and round of applause for Kuba. He's gonna be talking about Git, databases and indexes and interesting stuff. So round of applause for him.
Hello, I'm Kuba. I work at Sourced, mainly on projects related to storage and data processing, like MySQL Server and Git database and the engine. But also, in a spare time, I maintain a couple of open source projects like extended attributes package for Go and a zip compression library. And recently, I helped my friend in his new programming language called Never. But today, I want to talk about how we integrated the bitmap index in our Git database. So I have to give you first some context. So Git base is application, but it's just a front end. The real MySQL Server database engine, which is, by the way, powered by Vitess, is another open source project. Git base is so far just a read-only database, so no insert, no updates, and all the queries to Git repos are done by the Go Git package. The Pilosa is another open source project which we use. It's a distributed index implementation. It implements the roaring storage format, and apart from indexes, it lets you keep attributes in BoldDB. So the Git base is just a standalone like application which you can play with, just a front end. And all the well-known terms from the Git, like repositories, commit, refs, are mapped to the tables. And a convention is just how the reference are based on the convention, the naming convention. So basically, you can play with all the features like natural joins. And for instance, this query uses the natural join. So you want to get all the repositories where the Alan Turing contributed on a head reference. And so you just do the query from refs and natural join with commits. More sophisticated query is this one, which basically uses our predefined function, which lets you extract some abstract syntax tree and can recognize the language based on the content and stuff like that. So this query tries to extract all the identifiers, the identifier names from your Go files. But of course, we have indexes. Indexes are the most interesting for this talk. So we have indexes, and you can create an index on one or multiple columns. This is simple stuff. The nice thing is that you can specify what the index driver you want to use. So the red keyword, Pilosa, means that you want to use the Pilosa as an index driver. Also, you can create the indexes asynchronously and synchronously, but you can also, instead of creating the index on one or multiple columns, you also can create the index on an expression. So a little bit theory about the indexes till we dive in is that we have a hash indexes, which work like a hash maps. It's very good for equality. The most popular indexes in databases world are B trees, and in most places this is very good, the best approach. There are self-balanced trees, pretty well choice if you're wondering which one to use. R trees are not super popular. They are more to index multi-dimensional objects, so they are good when you try to group nearby objects. They are also self-balanced trees. And bitmaps. Bitmaps are very good to optimize logical operations. And this is what we chose for Git base. Bitmaps can be very expensive. To rebuild the whole bitmap, it takes some time. So it's a good choice for example, for read-only systems. Also, the best what you can get is when you have a lot of data, but not many possible values. And also the good thing about the bitmaps is that because it's optimized for logical operations, you can create a one bit index per column to satisfy all queries. If you don't have bitmaps indexes, the formula on the right is the number of indexes which you have to create to satisfy all the possible queries, where n is a number of columns. So, for example, B-trees, with the B-trees, you have to deal with this. So I mentioned a little bit about the storage storing, about the format, how it's stored. So it's called roaring format, and at Pilosa, which we use, they implement this in this format. And apart from all the offset which you have to set and headers in a file, the most important is how you store the data on a disk. So first, when you have the row ID and the column ID in your bitmap, you have to store to the local storage. So you calculate the position, you call the add function, and what add function does is basically the first byte is the operation. So in this case, it's a add. The next 8 bytes is a value in a little endian format, and the last 4 bytes is just a checksum of the operation and your value, and you write it to the disk. Basically, it's pretty simple how you save data, and Pilosa implements it. It's a typical, by default, it's a typical server client, but we hacked a little bit, which I will talk later. By default, it's a typical server client where communication goes over RPC or REST API. And the data model in Pilosa looks like this. So you have a huge Boolean matrix where index contains fields. And in rows in this matrix are local per field. But the columns are global. Columns are shared across all the fields. So you can say, give me column number 5 in the index, and you'll get all the ones or zeros from all the fields. But when you say row number 5, you have to specify for which field. So rows are local per field, and the columns are global. And nice thing about the bitmaps is that you can merge them. You can merge rows. But what's the most important is that you cannot merge rows across indexes. You have to merge rows inside the same index. So how we integrated the Pilosa in Git-base? So the first approach was the simplest one. Yeah? Take the Pilosa, run it in a container as a server, one Pilosa index maps to the one database index, and one field was equal to one expression, so the column, and it was super simple. We had to add the mapping, because you have to map, the bitmaps is just a matrix, so it has rows and columns, but you have to map the values to rows and columns to location or number of the record in your table. So it was the simplest approach. But after some time, we decided we don't want to maintain yet another server and troubleshoot all the synchronization problems and stuff like that. So we decided maybe it would be good to hack Pilosa a little bit and embed it into the Git base, so it let us run the Pilosa communicate with Pilosa like we communicate with the libraries. So this is what we did. We implemented yet another index driver. That time we called it Pilosa lib. We got rid of the server part, extracted API, and basically we tried to prototype some stuff. First of all, we had to deal with all the storage nodes. We had to open and close first. So like an index fields, and fields contains the views, and fragments can cache and stuff like that. But we found a holder, which was kind of the nice thing, because holder let you open the whole hierarchy just by calling the open and close thing, and it does all the thing for you. So sounded promising at the time, but suddenly appeared that we had so many problems and random crashes in this concurrent world with the holder. So we took a closer look how the holder was implemented. And apart from all the handlers and then the field, it contained two channels, open and closing. These two channels are only used in these two functions, open and close. And they close the open channel in an open function, and they close the closing channel in the closed function, what means that in a concurrent world, it's possible that you try to open already open file or close already closed file, and basically instead of do nothing or return the error, it panics. And please, I really like Pilosa, don't get me wrong, but if you are doing something like this, please don't. It's bad. It's bad by default. Nobody should do it. So how we solve this problem? We decided to get rid of the holder. It's the easiest way. So now we have to really manually open index and fields, but the opening and close functions for fields and indexes, they don't have this problem, that when you open, once again, nothing really bad happened. So yeah, so we got rid of the holder and we did some improvements. One of them is that we right now have one Pilosa index per table. So multiple database indexes are contained in a one Pilosa index. And one field is per index, expression, which can be the column name, and a partition. This is something what we introduced recently. Also what we improved a little bit, we still have the mapping in BoldDB, but we use the bucket sequencer to get the next possible available ID. It improved a little bit performance, but also we have to encode and decode data, so we use the GOP package from standard library. But what's the good thing about having one Pilosa index per table is that right now all your indexes are database indexes are inside one Pilosa index, so you can merge them. So how did it work, this merging stuff? So let's start from the scratch. You have to create the index. So first you have this huge Boolean matrix, and let's assume that we want to create the index on a column A and B. So you create the index, then you iterate through all the expression A and B, and for each of them you create the field. Let's assume for simplicity that it's the partition, just a one partition, and it's still the same index ID. So you create two fields, you have this huge matrix full of zeros. Then you have to populate it by data, so you iterate through columns, and every column, let's say, every column is a new record in your table. So it's kind of looks more or less like a column database. You iterate through the records and you iterate through the columns. So you put the one, you set the bit 1 in every column, but you have to figure out in which field and in which row. So you go to the field, which is mapped to your column, and try to get the row ID for your value. If value already exists, the getRowID function will return the row ID which already exists. If not, it will generate next ID for you. So after you get that, you set the bit in a field, and you put it in your put the location in your mapping. So this is how you save data, and then you have some ones in your matrix. So now you want to query. When you query, you put some filter, like you want to get all data where A is 2 and B is 4. So you do, once again, you iterate through the expressions, go through the fields, and then you have to find the row ID where the value 2 and the value 4 are. And for simplicity, let's say the value 2 is assigned to row 2 in A, and value 4 is assigned to row 4 in B. So at the end, when you already collected all the rows, which are assigned to your values, because it's an AND, you have to do intersection. So you intersect rows, and as a result, you get these columns where the one was on the same positions because it was intersection. So you get columns It's a 3 and a 5 as a result. You go to the mapping once again to get the location. Where are your records in your tables which were assigned to values 3 and 5. This is how the merging works. But what's worth to mention, in my opinion, what's the good thing about the bitmap indexes is the merging thing. And it doesn't make sense with bitmap indexes to create indexes on multiple columns. It's better to create a one index per column. The reason why is that if I created the index on columns A and B, so on 2 columns, then the index will be used only if I do intersections. And the intersection will be used as an internal operation first. But if I create the indexes independently, one index on A and second index on B, then I will get the same result. The intersection will be not internal operation, but the external operation later, but it will not have any bad impact on performance. But the good thing is that if you replace AND by OR, then it will do exactly the same. Instead of intersection, we'll just call the union, and that's it. So it doesn't make sense, because creating the index on multiple columns, it will only satisfy AND filters. So how it was done, because I mentioned that we have Pilosa and Pilosa Lib drivers, but it's also possible to implement own index driver, because everything what we did through the interfaces. And so first of all, you have an index driver interface, which just has these basic functions which let you create, load, save, and delete index. And this function returns the index interface, which basically has 2 main functions, has and get, which can answer your question, do I have this value? And if I have the value, you can get the value. And to get the value, we call the function get. It returns index lookup, which more or less is kind of a wrapper on a value iterator. Also, we have some indexes which let us query by ranges, like an Aston index, so you can ask questions greater, less than, etc. But they also, all of them, they return the index lookup. And the index lookup, as I mentioned, is kind of the wrapper on an iterator. It just gives you the iterator based on the partition. But the index lookup may implement set operation interface, and if you implement set operation interface, then you can merge lookups by intersection, union, and difference. As a result, you will get another lookup and get the values. So this is how merging works. And the last but not least is mapping. Mapping is important because basically with the bitmap indexes, you have just the row and columns, so you have to map values and records to columns and row IDs. So the mapping works like this. You want to get the row ID for your value. Rows are local per field, so you have to specify in which field. You pass the value, so first we encode the value by GOP encoder, and then we get the bucket in a bold DB which is assigned to the field, and we try to get the value from the bucket. If it exists, then we immediately can return the ID, row ID. If it doesn't exist, we take a next available row ID, calling this next sequence, and we once again encode it to the little endian format, and we put it in a bucket for bold DB, and of course return from the function. So this is basically how it works. Similar function is to get the location from column ID. Instead of encoding, we decoding columns IDs to get the location, and this is basically how it works. So maybe I can demo some stuff if I have a time. It's like a 5 minutes left. If you have, it's a question, like, do you have any questions, or I can demo something how merging works? Because what can go wrong with the live demo with 500 people in front of and live streaming? Nothing bad can make happen. So demo or questions? Demo. Okay. La la la. Okay. Bigger? Yeah. Really? Say stop. Okay, I think I already compiled it. So server, Git-based server. I have some small repo. Here in repos, indexes will go. Indexes, okay. Okay. I put it some debug functions so we can see here how it works. Basically, I'm still debugging with print lines. I don't know how many of you likes debugging with print lines. Yeah, and I mean, it's like we are passing almost first quarter of the 21st century, but we are still debugging with print lines. I really like Delph, and I hope Derek will tell me how about improvements on Mac OS, but so far, print lines also save my day. So, okay. All right. May I put it? Okay. So MySQL shell. No password for root, right? Okay, let me open. I have some scripts. Which can... Okay, so first of all, I would like to show you one of the tables, which is, can you see something? So I will test against some table which is called commit files, and it contains like a couple like repository ID, commit hash, file hash, and you have just a one repo called basic, and it has tons of stuff. So right now, thank you. So right now I will create the index. First index. Okay, 3 indexes. A, B on columns, on 2 columns, and A on 1 column and B on the second column. Okay, and this is how this debugging works. So basically, it creates the fields in your index, and it populates by data, and these numbers are, so every row has these numbers, and these numbers say in which column the one was set. Because I increased the font so much, so I don't know if what I want to say, if it's... So here, for example, we have a field which is assigned to the file path in index A, B, but if you go to the field which is also file path but in index A or B, it will have the same data. So basically, having also indexes on 2 columns and on just on 1 column, it duplicates data. So it's better, instead of duplicating data, create the 1 index per column. And so let's say we want to use this select to get the commit, to get everything where the commit hash is this and file path is that, and we call explain to explain how the query will work, and it says it will use indexes A, B. If I replace and by or, it will use indexes just A and B. So the reason why I said that it's better to have independent indexes is that I can drop the index on AB I can drop, and once again call explain, and this time 2 indexes will be used instead of 1 because I dropped the AB. So right now we can use indexes A and B independently, and it will also work with OR. Okay, last thing is that let me query. It queried, it gave result, and this is how it worked. We get 2 rows from the bitmaps. We intersect them. So the only position 0 is the position where in both bitmaps where 1 was set. So we get just a column 1, and as a result, it should be just one record. Where is it? Okay, and this one. I'm done. I'm run out of time. I'm sorry. That's it. Thank you.
Perfect. Thank you. Hey, how are you? Long time no see. Are you here?
Yeah, I know.
Yeah, I'm ready for your talk.
Hopefully,
Oh, yeah. Who said, where do you go? I start to be hungry.
Me too.
Oh, yeah. I mean, or
It is my money.
yeah, tomorrow.
I have like 70.
Yeah, but did you
I know, I know. I've been here inside for a long time.
So would you like an apple or
I don't think you want to share that.
I may not handle lunch breaks. Because if we do this, all of us then.
How are you going to use or
It's simple. I asked her, she's a Victor, and we sent them out with my money food. That's how we can do it. Because we have to stay there. Now we're going to reject it. Oh, thank you. Now I don't need sauce for the next 2 weeks.
Alright, so white logo? What is this? No, these. I don't know what this is called.
Do you have a Brussels scope? Do you have a... I don't give up.
You have a nice collection of
What else am I gonna say? Food.
You know which one?
Francesca, employee, boss, VP of products. I'm sorry, I'm shout this game, but
I don't want to interrupt them, like I don't want to be the rude person, just yelling, Francis,
wait, shout this name wrong.
come here.
What do you want for foods?
What?
Foods.
Oh, yeah, you got some fruit.
Oh, do you have? I'm not filled with an apple today.
Huh?
I'm not. I haven't only eaten this morning. I was filled with an apple.
I got this. I like this. Whatever you
Tabule is perfect for me, and I like that.
What's going out of the spoon?
Oh, I'll figure it out. Don't worry.
Good night. Just put it there.